many mathematicians who are experts in p-Adic numbers. So today I'm going to talk about some work that I have been doing with a set of various collaborators in the past couple of years, and so the idea or the hope is that we hope to understand whether tensor network is the right microscopic description of the ADS-CFT correspondence. And if it is, how do things like Einstein equation emerges from the tensor network? So in 3 years ago, with Wei and Charles, we constructed a tensor network that appears to be a very good description of the p-Adic CFT, and it has an interpretation of some scalar field theory in the Perturbation tree, which I'm going to talk about. And more recently, with my postdoc Xirong and with my student Xirong and my postdoc Lin, we understood how to extract some Einstein equation that is encoded in this tensor network. So this is what this is something that we find very interesting, and this is what I hope I will be able to share with the audience. Okay. So, my talk, I will start with describing the tensor network, why it is related to the ADS-CFT correspondence. I'll motivate why we're doing this in the first place. Then I will talk about the precise construction of this p-Adic tensor network and how to describe a deformed Perturbation tree out of this tensor network. And as we're going to see, this banded tree is related to some renormalization group flow of the p-Adic CFT. And from this RG flow, we're going to extract an Einstein equation out of it. Then I'll end with some summary and outlook of what we're doing. Okay, so why tensor network? So I hope the whole sort of a holy grail in fundamental theoretical physics is to understand how to understand quantum gravity. But what do we mean by quantum gravity? When we say quantum, we probably mean that we need some kind of algebra. And when we talk about gravity, it means that there's some kind of geometry hidden in this algebra. So as we all know, to understand quantum gravity, to introduce this algebra, canonical quantization has failed. So there's this divergence all over the place, and we don't really know where to find a proper set of algebra that is appropriate for gravity. So the ADS-CFT correspondence becomes a pretty interesting set of insights that might be telling us what the appropriate set of algebra should be like. Why is this? Because as I'm going to give, in case it is not something that is familiar to everyone, I'm going to give a very lightning detour to introduce the ADS-CFT. But basically, the ADS-CFT correspondence says some conformal field theory, no gravity, just a conformal field theory, is secretly the same or dual to a gravitational theory in anti-de Sitter space. This gravitational theory, it contains gravity for certain, but it probably also contains other things like matter, gauge fields, and so on. But nonetheless, it definitely contains gravity. So if this correspondence is true, then it would tell us it would give us hints of what this algebra is, because we know what is the algebra describing a CFT. It's not so mysterious what a CFT is. We know the Hilbert space, OP coefficients, and so on. And the ADS-CFT correspondence is telling us that by knowing what the CFT is, we should know how to describe gravity. But this is not really that useful And because we're just replacing one simple question, one difficult question by another very difficult question. That is, even if ADS is the same, the gravitational theory is the same as the conformal field theory, what exactly is the linear map, the map between CFT observables and gravitational observables? We have no idea, and therefore we are still basically as stuck as ever. Now, the Rudek-Yanagi formula that was proposed in 2006 gives us a lot of insights into how to recover things in the gravitational theory from things in the conformal field theory. What it says is that the entanglement entropy of the CFT, which is an algebraic object, depends on properties of states in the CFT, is related to the area of a minimal surface in ADS space. So with appropriate boundary conditions. And so this is one very immediate direct correspondence between algebraic data and geometry, minimal surface, right? Okay, and this inspired us a very beautiful observation by Brian Swingle, back then a grad student in 2012. So what he observed is that being a condensed matter theorist working on tensor networks, he has seen something that looks very similar to the Rudek-Yanagi formula before. So what he observed is that when one tensor networks are basically numerical methods to construct wave functions in many-body systems. I'm going to say a few things about it, a few more things about it. But the bottom line is, when we want to compute the entanglement entropy of a wave function, it would correspond to some kind of minimal cuts in the tensor network. And so in that regard, the Rudek-Yanagi formula looks very, very similar to to tensor network, and that was the reason why it led to the relations between proposals that tensor network might be the correct microscopic might be the microscopic explanation of why the ADS-CFT correspondence works, namely that the gravitational theory is some kind of a continuous form of tensor networks which turn entanglement data into geometrical data. Entanglement data, you could think of it as entanglement entropy, but more broadly speaking, it's the correlation of the CFT is encoded geometrically. So that is the essence of the tensor network program. So let me give a quick detour discussing what exactly is ADS-CFT, what are the basic ingredients, because these are some things that we're going to use later in the talk. So the ADS-CFT correspondence says, okay, if you have a d-dimensional CFT, then it is dual to some gravitational theory in one higher dimensions. So namely, some ADS d+1 dimension geometry. The conformal symmetry of this CFT would corresponds to the geometrical isometry of the gravitational theory. Moreover, the partition function of the conformal field theory would corresponds to the path integral in this ADS space. And a scalar field would correspond, a scalar field in the CFT would it would be in one-to-one correspondence would be in one-to-one correspondence with some scalar fields in the gravitational bulk, and the conformal dimension of these primary operators in the conformal field theory would control the mass of these scalar fields in the bulk. So particularly if I want to compute correlation functions of the CFT, then I would go about computing those in the gravitational theory by computing these so-called Witten diagrams, where I basically look for the propagators with appropriate boundary conditions in the ADS geometry, and I put together something that looks like Feynman diagrams with appropriate boundary conditions. Namely, these propagators go all the way to the boundary point of the ADS space. The boundary of ADS space, you can think of it as where the CFT lives. And if I have operator insertion at certain points in the CFT, then these propagators have to go all the way to these boundary points where operators are inserted. So these ingredients are important because that is how I'm going to use this knowledge to understand the tensor network. But these and moreover, let me also say that this dictionary was guessed a long time ago based on symmetries, isometries of the gravitational theory and conformal symmetries. By comparing how things transform on two sides, they managed to obtain these correspondence, the dictionary. Okay, this is so much about ADS-CFT. What about tensor networks? So in case it is not completely familiar, tensor network, as I mentioned already 2 slides ago, it's a numerical method to obtain efficiently ground states of some given Hamiltonian, or some many-body Hamiltonian. So suppose I have an n-spin system, then the wave function of this n-spin system would look as follows, with n, and this is amplitude for each basis, and there would be n indices. So if and each spin, it might be d-dimensional. If it is a spin half, then d is equals to 2, but in general, it could be d dimensions. And so in order to specify the wave function of a d-site wave function, I would have to specify basically d to the power n numbers in order to understand this wave function. But clearly that is way too inefficient. And so what people have done in the tensor network people, what they have done is to introduce an ansatz to write down this wave function. They break down this wave function into little pieces, and these little pieces, they have to introduce extra indices. So here I introduce new rho blah blah blah. This is not already in the original wave function, but in order that I'm describing the original wave function, these extra indices have to be contracted. So apparently it would look very complicated because we have introduced many new indices and then we contract them. But the point is, by writing such an ansatz down, for example, in this specific ansatz, it would each of these pieces carry one physical index. It's a very specific ansatz, but okay, in this case, each piece carry one physical index, and so altogether, to recover this wave function, I have n pieces, and here I have got 3 indices on each piece that are contracted with their neighbors, and so here, if each of these index is also d-dimension, then specifying one such tensor would require d-cubed component. And if I have n of them, then the number of degrees of freedom I have to specify here is n d-cubed, which is linear in n. So we have essentially simplified a very complicated problem, exponentially hard in the number of sites, to something that is only linear or polynomial in the number of degrees of freedom. So the question then becomes, how do we pick this ansatz? So one very interesting way to understand this ansatz is to think of it, is to represent this ansatz in terms of a diagram. So each of these tensor, I can represent it by a vertex, and each of these indices is represented by links on this vertex. If two tensors share the same index and that index is contracted, we connect these 2 vertices by a line. And so the ansatz that I have written here really corresponds to this diagram. So in particular, you can look at this diagram and then you would realize, suppose I want to compute entanglement entropy of 2 links here with the rest of the region. What would be, can I have some estimate of the bound on the entanglement? It's very easy. You can see that if I cut these 2 lengths, which is at the boundary of this region with two sites, then these 2 sites would be completely decoupled from the rest of the region. Therefore, it is this boundary lengths that completely control the amount of entanglement between these 2 sites and the rest of the system. So the bond dimension, the dimension of these 2 indices at the boundary, let's say it's d, then 2 times log d is the upper bound of the entanglement entropy of these two sites with the rest of the system. And you can see that in this ansatz, if I increase the number of sites included, the entanglement is always bounded by the two lengths at the boundary. So the entanglement does not scale with system size. What that means is the choice of this ansatz has very specific entanglement property. And so that teaches you how to choose your ansatz. It tells you that depending on what kind of entanglement your system has, then you can choose your ansatz appropriately, and therefore the little region of Hilbert space that you're describing for each ansatz have a good chance of describing the wave function or the partition function that you're interested in if you know what the entanglement looks like, what the correlation looks like. And one other thing about the tensor network is the data about entanglement is turned into geometry. It becomes the connectivity of these dots in this diagram, and it tells you everything there is to know about the entanglement, the correlation property of the wave function. And so this is the underlying reason why we believe the ADS-CFT correspondence and the tensor network are deeply related. The Rudek-Yanagi formula says entanglement is related to the shape of the geometry. The tensor network says entanglement is the connectivity of this graph. It's a geometrical data of this graph. And so in both cases, entanglement becomes geometry. And so this tells us that a tensor network might be the right thing to capture. It might capture some very important essence of the ADS-CFT correspondence. But so then the next question is, can we take the tensor network and try to see if the basic ingredients of the ADS-CFT correspondence, like the dictionary that I just described a couple slides ago, whether these things would re-emerge from a tensor network construction? If they re-emerge naturally, then I have reasons to believe that the tensor network really does capture the ADS-CFT correspondence. So what are the ingredients that I have to put in to be sure that I have got, I would be able to derive those ingredients? So first of all, I have to say what kind of graph I have to choose. Well, this is clearly question number one. After I've chosen the graph, then I have to say what kind of tensors, what the values of these tensors should they take to build this tensor network. And suppose I have chosen appropriate tensors to describe this conformal field theory, then I have to ask, can I read off some kind of bulk action, some bulk matter or bulk matter fields that is secretly encoded by the tensor network that lives in this discrete space. If I am able to do that, then furthermore, I would have to ask, can I assign some distance between any 2 points on this graph based on the data of the tensor network, based on the values of the tensors take that I've assigned? If I'm able to do all of that, then I can ask, okay, if I have notions of distance, then I can compute something like some discrete version of curvature on this graph. And because I have already understood what is the matter that is running around, that is described by the tensors, the matter that is encoded by the tensors that is secretly living in this graph, I can compute the stress tensor of this bulk matter, and then I can compare the curvature that I've assigned, and then compare with this expectation value of the stress tensor in the bulk, and then I could ask, are they the same? If they are, then I would say Einstein equation has emerged. It is secretly encoded in this tensor network. So from what I have said, it is clear that this is very difficult because I have made way too many guesses. And by the time I have finished guessing, it sounds pretty unlikely that anything accurate would be left. And so this is why I started working with the p-Adic ADS-CFT. because the p-Adic ADS-CFT is just way simpler. So initially, I tried to work with the continuous version of the ADS-CFT correspondence, and if you put things on a discrete graph, you break a lot of symmetries, the isometries of the ADS, and so it's very, very difficult to make progress when you break too many symmetries. And so here comes the Broodhound history and the p-Adic ADS-CFT. So in case it is not familiar to everyone what is the p-Adic ADS-CFT, let me give a one-slide review of what it is. So first of all, what is p-Adic CFT? So Meltzer back in the 80s gave an axiom to define the p-Adic CFT. But the idea is very simple. In the usual CFT, we have some fields, and the fields live in space-time. And the space-time coordinates are real numbers. In p-Adic CFT, the space-time, well, whether I should call that time anyway, think of it as Euclidean theory, the spatial coordinates are p-Adic numbers. And I think I don't have to explain what are p-Adic numbers to this audience, but they are rational. They are field completion of rational numbers. They can be expanded in this expansion. They have a different meaning for the norms, and the norms satisfy the axioms of distances and. So the bottom line is these spatial coordinates are p-Adic numbers. In a CFT, let's say in one-dimensional CFTs, under conformal transformation, x goes to ax plus b over cx plus d, where a, b, c, d forms this special linear group. And in the case of p-Adic CFT, x also goes to ax plus b, cx plus d, except that a, b, c, d are now p-Adic numbers, and they also form a group in the projective general linear group of QP. Then when you talk about real CFTs, you have to talk about the primary operators that transform covariantly under conformal transformation, and so you have to give a spectrum of these primary operators, and they transform in the following way. In the p-Adic CFT, they do exactly the same thing. You also give the spectrum, and they transform in a very similar way, except that you replace all the norms by p-Adic norms. Then, when you talk about this, given the spectrum, you also ask what happens if these operators get very close together. They can fuse, and to describe the fusion in real CFT, we have to specify their OP coefficients. In p-Adic CFT, we also specify their OP coefficients, but because of the properties of norms, which are locally constant, when we look into OP coefficients, fusions between operators, we will find that there's no notion of descendants, no derivatives can be very simply defined. Well, at least in Meltzer's version of p-Adic CFT, there are no descendants, and so the p-Adic, so the OPE expansion would appear as if they're only contributions from the primary operators, and it takes the following form, which is like the leading term in the real CFT, except here in the p-Adic CFT, that is everything. So we can then also compute correlation functions based on these symmetries and these properties, and two-point functions would look like x minus y to the power 2 delta. Delta is the conformal dimension of the operator, and three-point functions, it take this form. So for people familiar with CFT in real space, you will find that these correlation functions look exactly the same as what happens in real space, except you replace usual real norms by p-Adic norms. Okay, so that is so much about p-Adic CFT. The bottom line is specify the spectrum, specify their OP coefficients, then you get a p-Adic CFT. Okay, so what happens to the p-Adic ADS CFT? So the p-Adic ADS CFT was proposed by, I think, Gupser and his collaborators, and also Hideman and their collaborators back in the end of 2016, early 2017. So it is based on, so the idea is p-Adic CFT is probably also dual to some geometry. And the question is, what is geometry? In the case of a real CFT, we know that it is dual to some 8 antecedent space in one high dimension. So let's take the simplest example where we have a one-dimensional CFT. How should we understand this ADS space? We can understand it totally from conformal symmetries. So in one dimension, the conformal group is just SL2R, as I just described one slide ago. Then the isotopy group of SL2R is SO2R. And ADS space is actually just the quotient of the conformal group by its isotopy group. So now these Gupser and friends, and also Hideman and friends, they played the same game with p-Adic CFT. The conformal symmetry is PGL2QP, and the isotopy group here is PGL2ZP. And now let's take the quotient of these two things, and that gives you the Bruthard-Titz tree. And so this is the proposed bulk geometrical dual to p-Adic CFT. And so this is wonderful because the bulk that preserves all the conformal symmetry of the CFT is now a discrete geometry. So it is very, very tempting that if I want to construct a tensor network description of the p-Adic CFT, I'll just put a tensor network and cover this BT tree. And so there it is. That is what we did back in 2019. So we put a tensor network on this tree, and this tensor network, we constructed it so that it would describe the partition function of the CFT. So this is slightly different from the usual discussion in the literature where they talk about recovering the wave function of the CFT. Here we are directly constructing the partition function of the CFT or generating function of the CFT, because this is a p-Adic CFT. There's no notion of real time where we can construct wave functions, so it doesn't make a lot of sense to talk about wave functions. And so we're directly constructing the generating function. Generating function, I mean the generating function that can recover all the correlation functions of the p-Adic CFT. So how should we do that? So task number 1, I have to decide what kind of tensors to cover to be put on each of these vertex. So for simplicity, let's us consider p equals 2, p being a prime number, p equals 2. Then this would be the BT tree is a 2 would be a 2 plus 1, which is a 3-valent tree. 3-valent tree means every vertex has 3 legs. So what is the most natural CFT data that I can put here with 3 indices? The most natural thing that I could think of would be the OP coefficients of the CFT. So let us try to put the OP coefficients on every vertex of this BT tree. But that is not enough, because we know that we need to construct correlation functions, and correlation functions have delta dependence. So have conformal dimension dependence, and correlation functions have scaling behavior that depends on distance. And so we decided that when we contract neighboring tensors, so the labels would be labeled by primaries of the CFT because the tensors are OP coefficients, but when we contract the tensors, let's try to put a weight of p to the minus delta at every leg when we contract neighboring tensors. So that is for p equals 2. What happens if p is not 2? P is bigger than 2. What do we do with these tensors then? Then if we have more than with p is greater than 2, then we'll have p plus 1 legs here. We can just make it into a fusion tree where every vertex, so if we have p plus 1 legs in general, then we would just turn this guy into a sequence of fusion of these primaries. Because by consistency condition that were discussed by Meltzer, these fusion coefficients should be associative. Therefore, therefore it doesn't really matter the sequence of contracting or fusing these legs. And therefore, this gives you a consistent way of assigning tensors on every vertex for arbitrary p. And for every leg, we still put a weight of p to the minus delta there. But for simplicity, let's just focus on the tree where p equals 2, where every vertex has 3 legs. So if we put these tensors on this tree, there's a boundary, a symptotic boundary.
Could I ask a question for clarification, please?
Yes.
Actually, I mean, I'm not familiar. Can you hear me?
Yes.
I'm not familiar with the technique of this tensor networks, but from what you explained, you put the tensor network on the conformal field theory, right?
That's right. I put the tensor network on this
for a configuration which is in the conformal field theory.
I want to reconstruct the conformal field theory.
Yes. So in this case, the conformal field theory is on the boundary on the p-Adic line or p-Adic field. But you have the tensors at the vertices of the tree, which is kind of the bulk, right? So could you explain
No. Sorry. I think so. I haven't told you. So the usual way of talking about ADS CFT, people would say the CFT lives at the boundary of ADS space. But this is not what. So here, let's try to put that story aside. So now what I want to do is to reconstruct the partition function of the CFT. I just want to recreate the CFT. Forget about ADS for the moment. ADS or the BD tree here now is just a tool for me to recover the CFT. It's very much like when people talk about the tensor network to reconstruct wave functions of some many-body system, the graph chosen is just some suitable graph that has the right correlation properties. As we are going to see, the BD tree is some auxiliary space that captures the right correlation of the CFT. So we shouldn't think of the CFT as living at the boundary or in the bulk. Here, I just have a tensor network that is constructed to recover everything there is to recover about the CFT, as we are going to see. But you're right. I should say that this tensor network or the BD tree has the asymptotic boundary, and at the asymptotic boundary, you recover the QP line. Very much like in the case of ADS2, it also has an asymptotic boundary, and that asymptotic boundary is the real line. So when you put a tensor network on the BD tree, this is an infinite tree, and so we have to cut it off somewhere. And so we cut it off pretty close, very far away, pretty close to the asymptotic boundary. And so there would be some dangling legs that are not contracted with each other. And in order to recover a partition function, which is a number, you have to specify what kind of boundary conditions you take on these boundary legs. So here, because the bulk tensors, I've already taken them to be fusion coefficients. So every leg, every label is a primary. So what I'm going to do at the boundary is to choose every leg to be the identity label. So if all the boundary is the identity leg, then you can see that 0 identity would fuse to get identity again. So if all the boundary legs are just identity, this tensor network just give you the number 1 is normalized. Now what happens if I want to insert operator? I want to compute correlation functions of the CFT. I want to insert some operators at x1 and x2. So let's say this point is x1 and this point is x2. Then I change the boundary condition at precisely x1 and x2 to the labels corresponding to the operator that I want to insert. So look at what would happen here. On the legs that where no operator inserted, it is still projected to identity. So here I would have O1 fused with identity gives me identity again. And this is identity fused with this O1 operator, it gives me O1 again. And similarly here, identity fused with O2, I get identity. But then every leg, remember, I put in a weight of p to the minus delta. And so what is the value of these 2-point correlation functions? I basically keep collecting these factors of p to the minus delta, and the number of this factor is exactly equals to the geodesic distance in the tree that connects x1 and x2. Now, So I get the correlation function is basically proportional to function of this guy, p to the minus delta d, and d is the distance between 2 points on the tree. What is this function? This function is the Green's function of a scalar field theory in the BT tree. So I'm reading off something from the tensor network, but the answer is equal to the solution of Klein-Gordon equation of a scalar field living on this graph, where the mass of this scalar field is related to the conformal dimension of this boundary operator. Moreover, I say, okay, when I try to compute 2-point functions, I get this function that is p to the minus delta d. And it is a property of this BT tree where this guy is exactly proportional up to some normalization coefficients that we have to decide, but I will not talk about the details here, but up to some appropriate normalization. This object here, when V1 and V2 are basically 2 points at the boundary at x1 and x2, this guy is exactly equals to 1 over x is exactly this object, p to the minus delta d, where d is the geodistance. This distance gives precisely the 2-point function of the p-Adic 2-point correlators. And so what we have got here is very interesting. We have First of all, we say our tensor network, the way we constructed it, recovered the correlation functions of the p-Adic CFT. But while computing this result from this tensor network, we see that the way things works is such that it is encoding a scalar field living in the BT tree. So you can do the same thing with 3-point correlations. You say, then I would replace the boundary conditions at 3 different points by the appropriate operator that I want to insert, and then I would see the same issue, the same pattern. Operator, views of identity, I go down one step and until they meet. But before they meet, I will be collecting basically 3 pieces that are basically given by p to the minus delta d, where d is the distance from the boundary point all the way to the point where they meet. And so it looks like what we call Witten diagrams that I told you here. When we compute correlation functions of the boundary theory, it corresponds almost like putting together Green's function of multiple scalar fields that lives in the bulk, and then they meet at some interaction vertex. But each of this link here are Green's function propagators of that naturally lives in the BT tree. And so this piece of the ADS-CFT dictionary that were known in the field for a long time, it naturally emerges in the tensor network. And so we are now able to read off some effective action that describes some scalar fields that lives in the BT tree that is encoded by the tensor network that would compute correlation functions of the boundary theory. So this is point number 1. Now, so far everything lives in pure BT tree. Now I want to deform this geometry. I want to bend this tree. How am I going to do that? And we were inspired by the notion of renormalization group flow in ADS-CFT. How do we do renormalization group flow in ADS-CFT? Usually what we do is that we have some matter fields in the bulk and we change their boundary conditions. If we change their boundary conditions, usually the scalar fields would be turned on and they would have acquired non-trivial expectation values, and then we would take these expectation values and back react on the geometry. So this is what usually works in the ADS-CFT. Now I don't have ADS-CFT, I only have a tensor network, but I also have to impose boundary conditions. Why don't we change the boundary conditions from projecting everything to the identity operator to identity plus something else? Now you see that if I change the boundary conditions, indeed my tensor network is starting to describe something that is definitely not pure Brudt-Hutted space. How do we see that? Now, remember, every vertex is a fusion vertex. And so 0 identity is a fixed point of this fusion tree because 0 fused with 0 gives you 0 again, 0, 0 again, 0. But now if you have 0 plus something, then you can see that if I start with 0 plus something, 0 plus something, they fuse, you get 0 plus some other things. And then when you have 0 plus some other things fused with 0 plus some other things, you get 0 plus some other things. So you see, the contribution to the partition function or the generating function of this when I change the boundary conditions is different at different parts of the tree. Previously, when I put in boundary conditions corresponding to fixed point of this fusion tree, then every single vertex on this tree contributes equally to the final value of the partition function. But once I change the boundary conditions, different vertices contribute differently to the partition function of the tree. Therefore, just by changing boundary conditions, I have broken the isometry of this tree. And now it looks like different parts of the tree is doing different things. And so the question is, if that is the case, how do I assign distances between 2 points connected by a link? Previously, things are very simple because every vertex contributes this in the same way. When the boundary condition is 0, every vertex are the same, and therefore I can just say every link are the same. Distances is equals to 1 at every link. But now distances must be different at different position on this tree. So now we're given the question, how do we assign distance based on the values of the vertices when they contribute to the partition function? And if I have this non-trivial boundary conditions, in what way I can read off the expectation value of stress tensor? And if I am able to read off distance and expectation value of stress tensor of the matter that we have seen in previous slides, then I can compare these two things and see if some Einstein equation exists. Okay, so this was done with my postdoc Lin and with my student Shiro in the past 1 year and a half, really. So we studied this RG flow carefully, and we realized that indeed there is an Einstein equation that is secretly encoded in this data. So how did we go about it? So first of all, I have to tell you, how do we describe expectation values of scalar fields? What do we mean by bulk expectation values? So actually, we made a proposal of how to define bulk operator insertion back in our 2019 paper. So the idea is that, remember, this is a fusion tree. So we propose that inserting an operator in the bulk correspond to inserting a leg and fusing it with the rest of fusing it on this vertex with the other with the existing tensors. Why is this a good proposal? Because let's say if I insert an operator here when the boundary conditions are all 0, then I can immediately see that the expectation value of this field must be 0 because I have 0, 0 fused with this. Let's say this is A, then this will also be A, but the rest everywhere else is 0. So there's nowhere this A line could end. And so the expectation value must be 0. This is as expected in pure Brute-Hurwitz tree, pure geometry. We don't expect any expectation value for scalar fields. And if we insert two phi's, one here, then you can see that this A line could end on this other line. And the value of these 2-point functions would be proportional, again, to p minus delta d, where d is the distance separating this vertex and that vertex. That would be the Green's function of a scalar field. So this proposal, proposal for how operator are inserted would match with an effective field theory result. And so we propose that this is how we read off expectation values with how we insert operators in the bulk that is consistent with this an effective theory. Effective field theory that lives on this tree. So now when we have non-trivial boundary conditions, we can do the same thing. The expectation value of an operator at a certain vertex corresponds to fusing this operator there. Well, if the boundary condition is too general, it's very difficult to make progress. So we'll do some perturbation theory. Remember, when all the boundary condition is identity operator, things are simple. So now let's try to start with identity plus a little bit of some other things. So each of these j is identity plus a little bit of other things, and we're going to do perturbation here. Then what is going to be the expectation value of when we insert an extra leg at this vertex? You can see that to linear order in this perturbation, then basically every single leg can have an A that connects with this A that I have inserted. And so that corresponds to some Green's function propagator from the boundary to this point, but I have to sum over the contribution from all the points at the boundary, which is exactly what this term is. And for people familiar with the ADS-CFT correspondence, you recognize this is exactly how we compute expectation value of a bulk field when there is some non-trivial boundary insertions. Now you can compute second order in the boundary perturbation, and that would correspond to having multiple propagators that come to this point. Okay, so we can set up perturbation theory order by order in this boundary perturbation. And so the expectation value of bulk scalar fields can be computed. So now what do we have to do? There are several steps. Let's focus on step number 3. We read off bulk expectation values of bulk fields we can do. And we also have written down the effective bulk matter action. We talked about that multiple slides ago. Just by inspecting correlation functions that you read off from the tensor network, it tells you that it is encoding a bulk scalar field. Bulk matter fields, and from this bulk matter fields, we have to covariantize it because what we have read of lives in the pure BT tree. Now we are bending the tree, but perturbatively, we have to say how this bulk matter couples with the geometry. I'll talk about that slightly later, but we roughly know what the effective bulk matter action is. We know what the bulk expectation values is, so we can almost compute expectation value of a stress tensor that comes from this effective bulk matter action encoded by the tensor network. The next step is to assign distance to the edges and also to compute curvature. What is this? Then we have to assign curvatures once we have computed the distance of the edges. Now this is really difficult. How do I assign distance to 2 points on this tree given these boundary conditions? The answer is I don't really know. If I don't, what I know is that when all the boundary conditions is projected to the identity operator, all the distances is 1. And so when I turn on different boundary conditions perturbatively, I know that the distances at each edge becomes 1 plus a little bit of something else. I don't know what that something else is, but I know it is 1 plus a little bit of something else. And it also admits a perturbative expansion. So when I don't know what something else is, let's just parameterize how much we don't know about it. And so this is the next thing that we did. So the distance is 1 plus a something. Plus a little bit of something. So this is the little bit of something that is deviated from identity. And it would admit an expansion in the boundary conditions. So what are these things? So if you look at this tree, as I mentioned before, when you start with, let's say I want to inspect this edge. So what kind of data do I see in this edge? You can see that this edge, this vertex here, it connects to 2 vertex, and this vertex here corresponds to a bunch of tensors above it. And so what kind of data do I really get on this edge? It's nothing but these tensors contracting up until this point. And also on the other vertex, I have all the other tensors contracting, and then leaving some dangling legs here. Right, this would be some local data that is completely special to this edge, right? I would call these 2 vectors V on one side, where after I contract all the tensors above it, and V tilde, which is the which is defined on the other. Which is defined on the other edge after I contract all the other tensors up to this point. So when you have something dangling, then it would be a vector. And so every single edge, clearly there are exactly two vectors that is related to this edge. And so and because I'm doing some perturbation, these vectors that are at each vertex would be very close to being identity. Remember, if the boundary conditions are all identity operator, then everywhere everything is identity. So these vectors that came from contracting all the tensors before it, it would be very close to identity plus a little bit of something else. The V tilde came from contracting tensors on the other side. It would also be very close to identity plus a little bit of something else. But of course, this little bit of something else depends on what precisely on what my boundary condition is, and at every different edge, this omega and omega tilde would be different because it is of different distances from the cutoff surface. But otherwise, I know that there is such an expansion, and it characterizes an edge. And so it is most natural. If I don't know what the edge is, then I would expect that the edge is just some local, it just depends on these two pieces of data that is characterizing this edge. And it would admit an expansion, a power series expansion in this small stuff. And so let's just parameterize this power series expansion by the linear term, the quadratic term, and all the things that I do know about these numbers is that the dependence on this edge, on this data on the tensor network should be symmetric. It should be isotropic. It shouldn't specify which direction. It should just depends on this local data symmetrically. And so that is the only constraints that I can give to this little a, to this A and B and so on. But there's some power series. I don't know what the coefficients is. All I know is that it depends locally on the tensor network data. And once I have this expansion, I can also ask, what is curvature? I don't really know what is curvature, but I know that it should have a regular expansion when the distance is perturbed a little bit away from 1. So, okay, it is some perturbative series in this little j. So what do I mean here? Let me say one more word. So when I say the curvature of R, I mean the curvature R, I mean I'm talking about a small patch. So let's say I look at this vertex and I want to compute the curvature surrounding this vertex. Then what are the data available? I have distances on this edge, this edge, this edge, this edge that is connected to this vertex, this patch. And so I would expect that whatever however curvature should be defined, the curvature should be a function of this edge distance that is connected to this vertex. And so I don't know how the precise dependence should look like. Then I again do some expansion. But this expansion should respect symmetry or isotropy. Every edge that is connected to this vertex should contribute symmetrically to what I call the curvature that is surrounding this little patch, surrounding this vertex x. So I don't know what these numbers are, but I know that this expansion should make sense. Okay, so now I have distance as a power series expansion, the curvature as a power series expansion in J, which in turn is a power series expansion of this stuff. And I have my effective action, which contains the kinetic term and the mass term and interaction terms. I have to covariantize it to tell how it depends on distances. But so the kinetic term, so the mass term, I know that it should depend on, there should be some volume form. And so D here is the edge distance, which will play the role of the volume form. And here we have a kinetic term. So supposedly there is a volume form, but I might also have some G inverse mu nu because this is a kinetic term. I don't exactly know how it works. So let's say it depends on the edge distance D to some power K that I don't know what it is. And similarly in the interaction term, I know that this interaction vertices should be proportional to the OP coefficients, but let's us pretend that I don't know what they are yet, and that the dependence on the they should also couple to the edge lengths, and this edge dependence, I don't know what they are. Again, because I know what happens when all the distances are equals to 1, but when the distances are perturbed away from 1, I'm not entirely sure what they are. Then I have to parameterize them. Sorry, I know I'm running out of time. So let me try to finish very quickly. So after having proposed, parameterize this expansion everywhere, lots of coefficients, I don't know, then I can say, okay, what is the Einstein equation when I vary these actions built from the curvature and the matter and from the tensor network. So I can vary this effective action that I don't really know what they are, with lots of unknown coefficients, and then I compare this G with T. I ask, what are the conditions if I insist that G plus T equals 0? What would I get? So you remember, all the boundary conditions are completely arbitrary. Yes? So all the boundary conditions are completely arbitrary. So if I insist that G plus T equals 0, I have many constraints on the unknown coefficients that I have. So let me put it this way, quickly, that there is a unique solution. Up to normalization, there's a unique solution to these coefficients that I put out, that's such that one Einstein equation can in fact be satisfied. And what is really nice about this solution is that, first of all, it says it is consistent with the relationship between the mass and the conformal dimension. And secondly, the values that you get for these when I parameterize the form of the curvature, so this B and C parameterization of the curvature, the solution of these coefficients tells me that the form of the curvature is precisely a graph Laplacian defined for these edges. And this is exactly to linear order. In the mathematics literature, people studied graph curvatures by Gubser and using previous results of Lin and Yao and a company. They found that to linear order in the most natural graph curvature, if you perturb away from the BT tree, it exactly takes this graph Laplacian form.
Time, you should finish. So.
Okay, so let me say, let me conclude here. We have the Einstein equation emerges in at least in the perturbable limit from the tensor network. So it looks like we're giving evidence that the tensor network is capturing some important ingredients of the ADS-CFT correspondence. Thank you very much. Sorry for being over time.
Thank you for the nice and interesting lecture. Are there any questions?
Could you please go back and display the previous slide that went too fast?
Here?
No, the ones that you didn't have time to talk about, rather than the thank you slide. Next.
You mean Outlook or?
Yes, please. Yeah, thank you.
So, do you mean I want to say something about it?
Well, that if the chair allows, I don't know. Otherwise, I'll just read it.
Sure. So I think one very important lesson that we have learned here is that we have one single tensor network. The assignment of the values of the tensors are already completely fixed, but it can still describe many different geometries depending on your boundary conditions. So you could ask, what kind of geometry are actually possible and not possible for one given set of tensors? Secondly, so this is what I meant by one tensor network and many worlds, and so right now, so this is actually connected to something that is very interesting, that what we call strange correlatives, and so basically there's some possibilities that we are able to generalize it to real CFTs by making connections between what we have now with some topological orders. So I don't know if you're familiar with this notion that in this tensor network, what we have made use of is an associative algebra in constructing this tensor network. And associative algebra or Frobenius algebra is naturally related to some two-dimensional TQFT. And this so we have some approximate two-dimensional TQFT recovering some one-dimensional CFT. And so we do have some idea how to make use of some high-dimensional fusion category, basically, to recover tensor networks that would describe CFT. So, but very unfortunately, I have no time to talk about that. But that is what I meant to say.
Okay, thank you.